They claim the James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The posts claim that the telescope captured the object changing its trajectory.
The James Webb Space Telescope just pulled off something absolutely incredible, capturing the first real image of 3I Atlas, an ancient interstellar comet that's been traveling through space for potentially billions of years. This isn't just any space rock. It's a chemical time capsule from another star system, carrying secrets we've never seen before. The comet's composition is so extreme that it's breaking everything we thought we knew. But what if this visitor is older than our entire solar system? What cosmic messengers are heading our way? Webb's historic capture, the first real image of interstellar comet 3I Atlas. The moment astronomers at the James Webb Space Telescope received the data on August 6, 2025, they knew they were looking at something extraordinary. Every pixel in that infrared image whispered stories of distant worlds, a cosmic traveler that had journeyed across the vast emptiness between stars to visit our solar neighborhood. This wasn't just another space photograph. It was the first real image of 3I Atlas, an interstellar comet that had crossed unimaginable distances to deliver secrets from another stellar system directly to our doorstep. The discovery of 3I Atlas began in early July 2025, when the Atlas survey system detected something unusual moving against the backdrop of distant stars. This object immediately caught attention, because it represented only the third confirmed interstellar object ever detected in our cosmic neighborhood. The first two visitors, Oumuamua and 2I/Borisov, had already challenged our understanding of what might wander into our solar system, but both carried mysteries that left scientists with more questions than answers. Oumuamua defied simple classification with its strange acceleration and elongated shape, while 2I/Borisov, though clearly comet-like, still left many questions about its chemistry and origin unanswered. Now, 3I Atlas was approaching on a trajectory that would bring it within reach of our most powerful telescopes, and the race was on to capture it before it disappeared forever into the cosmic void. This visitor was moving at incredible speeds, traveling roughly 210,000 kilometers per hour through space on a hyperbolic path that would take it past our sun only once. Unlike comets born in our solar system, which follow predictable elliptical orbits, 3I Atlas was a one-time visitor, a messenger from distant stellar nurseries that would never return once it completed its flyby. Webb's technical masterpiece and precision targeting. The James Webb Space Telescope's successful capture of 3I Atlas represented a triumph of precision engineering and astronomical coordination, pushing the boundaries of what space telescopes can achieve. Using its near-infrared spectrograph, Webb managed to lock onto this faint-moving target across astronomical distances in what felt like threading a needle in the cosmic darkness. The technical challenge was immense because, from Webb's position at the second Lagrange point, 3I Atlas appeared as nothing more than a barely detectable speck racing against a shifting backdrop of stars. The team had to perform incredibly delicate calculations and precise trajectory modeling to ensure the comet would fall within Webb's narrow field of view, even as it hurtled inward toward the sun's. Success required not just capturing an image, but obtaining a complete spectral map of the comet's glowing shroud, the coma that surrounds its nucleus like a ghostly atmosphere. This achievement demonstrated that space telescopes could track and study even the most elusive cosmic visitors with unprecedented precision. What emerged from Webb's instruments transformed our understanding of interstellar objects completely. The image revealed a dense carbon dioxide-dominated coma radiating in infrared wavelengths between 0.6 and 5.3 micrometers. This wasn't just a pretty picture, but a detailed scientific document that would revolutionize our knowledge of visitors from other star systems. Within that ethereal glow, Webb detected signatures of multiple molecular species, including water vapor, carbon monoxide, water ice, dust, and trace molecules such as carbonyl sulfide, each telling part of the story of this cosmic wanderer's origin and evolution. The technical specifications of Webb's observation highlight the telescope's revolutionary capabilities in ways that ground-based observatories simply cannot match. Operating in the cold, dark environment of space, with unparalleled sensitivity in the infrared spectrum, Webb could tease out weak spectral lines, distinguish overlapping molecular features, and map brightness variations at fine spatial scales. Earth-based telescopes and even the Hubble Space Telescope struggle with sensitivity issues, background interference, and the inability to observe at long wavelengths, where many crucial molecular signals hide. Chemical revelations from another star system. The James Webb Space Telescope's spectral analysis of 3I Atlas revealed a chemical composition so extreme and unusual that it stunned astronomers. The most remarkable finding was the overwhelming amount of carbon dioxide dominating the comet's coma. With nearly 8 times more carbon dioxide than water vapor in the glowing gas cloud surrounding its nucleus, this ratio ranks among the highest ever seen in any comet. Such a discovery is forcing scientists to completely rethink how this cosmic traveler formed and evolved during its long interstellar voyage. In most comets from our solar system, water ice sublimation drives the show as they near the sun, creating the bright tails and halos we easily recognize. But 3I Atlas broke that pattern entirely. Its weak water signal hinted that something might be preventing heat from reaching its deeper layers. Perhaps an insulating crust of organic material, or an internal structure that limits heat flow keeps its water-rich core frozen, while carbon dioxide and carbon monoxide, which vaporize at lower temperatures, fuel the comet's visible activity instead. This unique chemical fingerprint acts like a time capsule from the comet's formation, evidence of conditions in a stellar nursery far different from where our sun was born. The balance of dust, gas, and ice in 3I Atlas's coma paints a picture of formation processes that took place around a different star, under distinct temperature and pressure conditions inside another protoplanetary disk with its own chemical makeup. If 3I Atlas formed near a carbon dioxide ice line in its original system, its birth environment must have contrasted sharply with the conditions that shaped comets in our own. Beyond its dominant carbon dioxide signature, Webb's observations also revealed a rich molecular mix, including water vapor, carbon monoxide, frozen water, various dust grains, and trace molecules such as carbonyl sulfide. Each of these components offers valuable clues about the comet's formation and the chemical transformations it experienced while drifting through interstellar space. The presence of so many different molecules shows that 3I Atlas managed to preserve a high level of chemical complexity. Despite the extreme environment of the cosmic void, the spatial patterns of these emissions also reveal important details about the comet's internal makeup and activity. Webb's images indicate that the gas seems to escape broadly from the sun-facing regions, rather than from a few isolated jets or vents. This widespread outgassing pattern points to either a highly porous interior that lets heat move easily through it, or to multiple active zones scattered across the surface, each contributing to the rich, continuous flow of gas and dust that defines 3I Atlas's glowing coma, physical mysteries, and structural puzzles. Figuring out the exact size and structure of 3I Atlas has proven to be a major challenge. Current estimates suggest its diameter lies somewhere between 1.4 and 5.6 kilometers. But that wide range creates big uncertainties. Size directly determines how much surface area is available for outgassing, how deeply heat can penetrate, and how efficiently it moves through the comet's interior. This ambiguity also makes it difficult to pin down the comet's mass and density, two key factors for understanding its internal strength and how it withstands external forces. What makes 3I Atlas especially intriguing is its mysterious resistance to recoil effects that usually influence active comets. Even though there's clear evidence of intense outgassing forming its bright coma, the comet shows virtually no measurable non-gravitational acceleration. Normally, jets of evaporating gas act like tiny thrusters that nudge a comet's orbit slightly. But in this case, 3I Atlas seems either massive enough or structurally strong enough that these forces barely affect it. This points to an object of extraordinary density, high internal cohesion, or a unique structure that minimizes any uneven push from escaping gases. Some models estimate the comet's mass at over 33 billion metric tons, though these numbers come with big uncertainties given how hard it is to measure such properties from Earth. If those estimates are close to correct, 3I Atlas would rank among the heaviest comets ever detected, which might explain why it shrugs off the usual effects of outgassing a nucleus at the larger end of its size range, several kilometers across, would possess enough inertia to stay stable against the gentle thrust from escaping gases. The comet's hyperbolic orbit adds another layer to its intrigue. It's one of the most extreme trajectories ever observed, confirming beyond doubt that 3I Atlas originated from interstellar space. Traveling at remarkable speed, it will sweep through our solar system only once before continuing its journey back into the void. Trajectory studies trace its incoming direction roughly toward the constellation Sagittarius, though pinpointing its exact birth star after billions of years of galactic motion is practically impossible. Even more curious is how early 3I Atlas became active, revealing yet another clue about its physical makeup. Unlike most comets that remain dormant until they move inside Jupiter's orbit, 3I Atlas started showing noticeable activity much farther from the Sun. This unusual early outgassing suggests that volatile ices with extremely low sublimation points began vaporizing even in weak sunlight. That behavior points either to a strange surface composition or to internal processes that are still poorly understood, continuing the puzzle of how this interstellar wanderer holds together and behaves so differently from any comet we've seen before. Ancient wanderer from deep cosmic time. The story of 3I Atlas stretches back through unimaginable cosmic time, with some estimates suggesting this interstellar wanderer may be between 3 and 11 billion years old, potentially predating our entire solar system. If these age estimates prove accurate, 3I Atlas would represent a fossil from the galaxy's early epochs, carrying within its frozen core the chemical memories of stellar environments that existed when the Milky Way was younger and perhaps dramatically different from its current configuration. The comet's exceptional velocity of approximately 210,000 kilometers per hour surpasses both Oumuamua and 2I/Borisov, implying a more ancient origin and a correspondingly longer interstellar journey. This tremendous speed suggests that whatever gravitational event ejected 3I Atlas from its parent system was particularly violent, perhaps involving close stellar encounters, massive planetary migrations, or the disruptive influence of passing binary star systems. Such dramatic ejection mechanisms tell us that interstellar comets are not gentle wanderers, but survivors of cosmic catastrophe. During its eons-long journey through the interstellar medium, 3I Atlas would have endured a harsh gauntlet of cosmic challenges that would destroy weaker objects. Cosmic rays would have bombarded its surface, potentially altering its chemical composition through nuclear reactions. Micrometeorite impacts would have gradually eroded its outer layers, while thermal cycling from encounters with stellar radiation fields would have stressed its internal structure. The fact that 3I Atlas retained sufficient volatile reserves to remain active today speaks to remarkable structural integrity, and perhaps protective mechanisms that shielded its interior from the worst effects of interstellar exposure. The comet may have passed through molecular clouds during its journey, regions of space where gas and dust densities are much higher than the typical interstellar medium. Such encounters could have added material to its surface or altered its composition through chemical interactions with the surrounding environment. Some of the organic compounds and trace species detected in its coma might reflect these interstellar processing events rather than its original formation conditions. The survival of deep volatile reservoirs within 3I Atlas provides a unique opportunity to study primordial materials that have remained relatively unaltered for billions of years. Unlike comets in our solar system that have made repeated trips past the Sun, gradually losing their most volatile components, 3I Atlas preserved its original chemistry in the deep freeze of interstellar space. When we analyze its coma composition, we are essentially reading a chemical memory book, written in an ancient stellar environment far from our Sun. Coordinated Multi-Observatory Campaign. The study of 3I Atlas stands out as one of the most extensive and well-coordinated multi-observatory efforts ever carried out for an interstellar object. Telescopes across the globe and in space worked together to capture every possible detail of this rare, cosmic traveler. This global teamwork was vital because no single telescope could gather all the information needed to fully understand such a complex and fast-changing object. Each observatory brought its own strengths, unique instruments, and wavelength coverage to help scientists assemble a complete picture of this visitor from another star system. The Hubble Space Telescope played a key role during its July 21, 2025 observations when 3I Atlas was about 277 million miles from Earth. Hubble's images revealed a striking teardrop-shaped dust envelope surrounding the nucleus, offering valuable insights into dust distribution, mass loss rates, and tail geometry that perfectly complemented Webb's detailed chemical data. Hubble's visible light view helped researchers understand how dust particles interact with solar radiation and how the comet's coma structure changes over time. Ground-based telescopes, including Gemini South and Gemini North, continuously tracked the comet's evolving tail and brightness as it moved closer to the Sun. These Earth-based observations provided vital time coverage to monitor quick changes in activity and tail formation, information that space telescopes, limited by observing schedules, might have missed. The blend of constant ground-based monitoring with precise space-based spectroscopy produced an unmatched dataset for studying interstellar objects. Archival research also proved invaluable in stretching the timeline of observations beyond the comet's official discovery. After astronomers spotted 3I Atlas in July 2025, they searched earlier sky surveys and found it in older images, taken weeks or even months before, when it was dimmer and farther from the Sun. This look back in time allowed scientists to trace its early activity and determine when sublimation began, giving crucial clues about its thermal properties and nucleus composition. The coordination behind this massive observing effort highlights how vital rapid communication and flexible scheduling have become in modern astronomy. When 3I Atlas was confirmed as an interstellar visitor, observatories worldwide quickly adapted their schedules for special target of opportunity observations. This swift response was essential, as interstellar objects move through our solar system so fast that any delay could mean missing key moments in their evolution. polarimetry, and unexpected chemical discoveries. Polarimetric studies of 3I Atlas have uncovered some of the most unusual optical behaviors ever recorded in a comet, adding yet another layer of intrigue to this already extraordinary traveler. Recent measurements of how sunlight scatters and becomes aligned reveal that 3I Atlas shows an exceptionally deep and narrow negative polarization branch. The degree of negative polarization reaches about 2.7% at small phase angles and flips around 17 degrees. This rare combination, a strong negative polarization at low angles coupled with a narrow inversion point, is almost unheard of among both asteroids and comets in our solar system. These remarkable polarimetric features suggest that the dust grains in 3I Atlas's coma interact with light in ways that differ dramatically from normal solar system materials. The grains may be unusually tiny, possess unique surface textures, or have a very porous structure that changes how they scatter sunlight. Such distinctive optical properties could mean that 3I Atlas belongs to an entirely new category of interstellar object, expanding our understanding of how dust and ice can form in planetary systems beyond our own. Detecting water in 3I Atlas required extremely careful work, using ultraviolet observations from the Neil Gehrels Swift Observatory. Scientists identified faint emissions from oxygen radicals typically linked to water-ice sublimation, which indicated a water production rate of roughly 40 kilograms per second when the comet was about 3.5 astronomical units from the Sun. Although this signal is weak compared to the comet's dominant carbon dioxide outgassing, it provides crucial evidence that water ice does exist within the nucleus, even if it contributes far less to its activity than it does in most comets from our solar system. This water detection implies that nearly 20% of 3I Atlas's surface could already be active at its current distance from the Sun, a surprisingly large fraction compared to many other comets. Such widespread activity may result from large icy grains within the coma that act as extended sources of water vapor, releasing molecules far from the nucleus as they sublimate under solar heating. Perhaps most fascinatingly, several telescope campaigns have reported signs of nickel in the coma of 3I Atlas, a metallic element rarely highlighted in comet studies. The detection of nickel suggests that some of the dust particles being released contain metallic or refractory inclusions, hinting at origins or processing in high-energy regions shaped by shock heating or metal-rich conditions in young protoplanetary disks. This metallic component, combined with the comet's strong carbon dioxide dominance over water, forms a chemical signature unlike anything ever observed in solar system comets.